Hello everyone, welcome to the lecture number 21 of this NPTEL lecture series on charging infrastructure, where we are dealing with different aspects of EV charging systems. In today's lecture, we will see flyback based PFC converters. In the previous discussions, we have seen boost converter based PFC converters, where we have diode bridge rectifier in the front end, and then followed by we have a DC-DC boost converter. So, and we can able to ensure the current drawn from the source is sinusoidal by ensuring that this ID, the average variation of this ID is having the rectified variation. If we ensure this is there, then automatically our current drawn from the source is also the unity power factor or the sine wave having a zero phase angle between the current and the voltage. Then we have seen its derivative, which is nothing but a bottom pole PFC, where we do not require any diode bridge at the first stage. We directly connect the inductor to the active bridges. Again, we can either use this diode one diode half bridge, or we can either use active half bridge, or you can say using active switches. Again, here the concept remains the same. We apply the voltage across inductor in such a manner that the average current drawn from the source is sinusoidal and having the unity power factor current drawn. So, this is what we have studied. We have also seen the average current control, where we were actually controlling the average value of the current drawn from the AC source. And then we have seen the voltage follower mode, where we have seen that converter will be in the DCM mode or discontinuous conduction mode, and by doing the discontinuous conduction mode, automatically the peak of the current will be having the sinusoidal variation, and that is when we can say that the average current is also be nearly closer sinusoidal variation. Now, the advantage with that is in DCM mode, the advantage is that DCM mode means discontinuous conduction mode. The advantage is we do not have to put any multiplier while doing the closed loop control. It is a simpler closed loop control. We can implement it in any controller, and also we do not need very high end controller to implement those DCM mode control. And the current will be having the voltage follower mode, where you do not require any multiplier or any high end computation. Now, one question can be asked, can only this be the method by which you can actually have the constant or regulated voltage at the output while drawing unity power factor current from the source? There are other methods also which can be used. For example, flyback based PFC converter. In flyback based PFC converter, what we have is we have the diode bridge rectifier at the front or the first stage. So, we have a diode bridge at the first stage, and then followed by what we have is we have the flyback based converter. That switch can be take, let us say define this as S1 switch, and here again we will define the dot polarity in such a manner that we have dot polarity here, and then this inductor is actually wounded on a core having another winding whose dot polarity are arranged in the manner shown over here, and then followed by this we will have a diode, let us say diode dV, and then we can have a capacitor C, and then finally we have a load resistance RL. And here we have the voltage, nothing but V0 voltage, which is coming over here, and we can define D1, D2, D3, D4. Let us take the inductor. These two inductor have the turns ratio in n raised to 1 ratio, where n is the winding. Let us say this winding name is P and this winding name is S. So, P has n number of turns while S has just one number of turns. And let us say if there is only one winding which is made over here, it has the inductance L, refer to the primary side of this transformer. And if you look very carefully, we again have this VD voltage which is coming over here, and we have again Vs voltage which is nothing but Vs peak sine omega t, and this Vd is nothing but modulus of Vs, which is nothing but the rectified AC at this across the diode bridge output. Now if you look very carefully in this particular circuit, these two inductors are wounded on the same core, that is why they are actually coupled together. And what happens is that again the same thing will happen. My duty ratio, which is the ratio of the time duration in the switching period, is the time during which this S1 is on, and in 1 minus dts period, 1 minus d of ts period, my dB will be on and S1 will be off. So here we have two state, since we have here rectified DC voltage here and output is your fixed DC, V0 is a fixed DC, we must ensure that this S1 has to be switched in such a manner that we are getting a constant voltage at the output. So again we have the duty ratio, which is we can define D of T, we have the D of T which is nothing but duty ratio of switch S1 that varies with time. Time t, and here again this switch S1 is switching with frequency FSW, where FSW is very much greater than Fs, where Fs is the line frequency, which is generally 50 hertz or 60 hertz. Now again we can apply the volt second balance on this coupled inductor. So here what we can do is we can now say that during D of t ts period, during this period the S1 is on. Now if we look very carefully, since the S1 is on, so our circuit will be, let me here just draw the Vd voltage, which is nothing but the modulus of Vs. What we have is we have something like inductor here, and this S1 switch is on. So since this S1 switch is on, S1 switch is on, so this S1 switch is on. Here we can, now this is the Vs, S1 switch is on, and here the dot polarity is here, and what we have is we have another dot polarity. So since the S1 switch is on, here we are directly applying Vd voltage, and since here Vd voltage is there, onto the coupled inductor, which is onto the other winding, which is actually bonded on the same core, what we have is we have plus minus polarity voltage coming over here, and then this, which results in, since the negative polarity is applying onto the anode of this diode, that is when this diode dB is open circuited or reverse bias, and what you have is we have a circuit something like this, where we see that our this capacitor C is nothing but actually supplying it to the load. And during this time we can say that during D of t ts period, we can say that the voltage applied across the inductor, we can say that VL is nothing but modulus of Vs, voltage applied during dt of ts period. Okay, so this is the thing during dt of Ts period. Now let us take the next case, how our circuit looks like when we have 1 minus d of Ts period when your S1 is off. During 1 minus d of Ts period, what happens is that my S1 is off, and let us say when S1 is off, let me draw from here Vd. Now S1 is open. Now because of this S1 is open, what happens is because this S1 is open, since this S1 is open, what happens is that the instant during which this S1 is open, what happens is that there is di dt which will be coming across this, which is in the negative direction. That means you have voltage induced in this way, which is nothing but V equal to L di dt, and because of this positive negative polarity, here we have a negative and positive polarity. That is when this diode dB is forward biased, and then you have the current which start flowing to the load in this manner. So here in the previous case, the current is going from dot to non dot, and thus as a result of which the flux in the core gets built up, while in this case again, in order to ensure the continuity, the current through the inductor cannot change. So that is why on the other winding the current will again start from dot to non dot. However, in this case, since there is no voltage source is been connected to the winding which actually build up the flux in the core, in this case it is the core which is actually driving the load, and that is when the flux in the core get de-energized. In the previous case it core was getting energized, in this case core will get de-energized, or the flux will then decay out, or you can say that the flux which was got builded in the core will now come back in such a manner that the flux will come back to its original point. The current will be such that we have the flux goes to 0, and we will be ready for the next cycle to have the again flux build up in the next cycle. So what we have is, in this case, in 1 minus dTs period, 1 minus dt of Ts period, the S1 is off, and because since that S1 is off, what is happening is that the dB is forward biased, and since these two windings are wounded on the same core, so using the first winding, the core onto which this first winding is wounded, the core will get energized, and using the second winding it will get de-energized and coming back to its original value to again start off in the next cycle, or have some average value which keeps on growing and then falling back to the 0 point. So this is forward biased, and we can say that core is de-energized as the flux in the core comes back or falling down. Because of this, as this will be feeding the power into the load. At that point, what voltage we are applying, if you look very carefully, during this time the voltage across this inductor, if I take this as n raised to 1, the voltage across this inductor is nothing but equal to, here we are applying the V0 voltage. So here if we take down to the primary side, the VL voltage applied onto this core or onto this winding is nothing but minus n times V naught. Why we have taken n? Because everything we are writing down with respect to the primary. So, because of this negative voltage applied across this inductor, the flux in the inductor will get decays down or comes back, the inductor current will have the negative slope. Now, because of these two things, what happens is that we can then apply volt second balance in half line cycle. Why I am saying half line cycle? Because this VD which is there will have the variation nothing but rectified DC, which actually varies in half the line cycle. So, if you take this one, this thing from here to here, it is T, which is nothing but 1 by Fs, and in half the line cycle it actually repeats itself. So, in half line cycle if you do, we can write 1 by T by 2, 0 to T by 2, D of T period applied for during this D of Ts period you have applied. Actually here again if I am writing this Ts, Ts is nothing but 1 by Fsw corresponds to the switching period. So, this volt second balance if we are doing this, and during this time we are having, if we see previously it was nothing but modulus Vs plus, so we can write down in 1 minus d Ts minus n V naught period d of t, and this entire things will actually becomes to 0 as we are doing the volt second in a half line cycle case. Now, this integration is very difficult to solve, but since we assume that f switching is very much greater than Fs or Fsw is very much greater than Fs, we can take approximation as we took in case of boost PFC case and can write d of t into Ts modulus Vs plus or minus n V naught minus d of t Ts is nothing but equal to 0. Again here it is the multiplication, not the negative sign is there. So, this is the thing. So, we will now in this particular case when we further rearrange this particular things, what we get is we get modulus Vs d of t, because this Ts will get cancelled out, and what we have is nothing but equal to n V naught 1 minus dt, and that when we rearrange, so this we will get modulus Vs d of t plus n V naught d of t n V naught, that implies d of t nothing but n V naught one plus modulus Vs by n V naught, and that modulus Vs is nothing but by n V naught. Now, this is the duty ratio of this switch S1, which has to be varied in this manner, then only we can ensure that output voltage is having the constant DC voltage, as here input we have the rectified DC and output we are getting the pure DC, which is nothing but equal to V naught, obviously over which you have, actually you have something like, if we draw, we have this V naught, this one, over which we have second line harmonics voltage coming over here like this, second line harmonic voltage. I mean we have the second line harmonic ripple riding over the capacitor. So, now from this rectified voltage which is going between 0 to Vs peak, from here till this point we are getting just by ensuring that this S1 switches in with a duty ratio, that means a fraction of the period in the switching period by this particular variation. Now if we try to see this particular duty ratio, if we vary, we get the constant output voltage. Now to ensure the unity power factor current drawn from the source, one simpler method we can do is we can opt for DCM operation of flyback based PFC converter. So in this case, let us see what is discontinuous operation of flyback based PFC converter. So in this, let us try to draw the inductor current. So this is T, this is IL of T. Now this IL of T is something referred to primary side. That means you can say that it is here. I am drawing IL of T. Now if you draw IL of T, since in the DTS period it is applied, you are having the voltage, positive voltage modulus Vs, and since because obviously a positive quantity, so what we will see is that we have a rising slope which goes up to here, and which has the slope nothing but equal to modulus Vs by L, and during the discharging period or during the the current negative slope period is happening when we have 1 minus DTS phase, where minus and V naught voltage is applied across the secondary winding of the inductor. So we can write down the IL, or you can say that IL of T, or you can say the IL secondary. Let us define this. This is nothing but I secondary. So we can write I secondary is will be starting from here, and then it will have a current which comes down here. Then again after certain point, my this current will again start from here, comes back, and then here my IS will go down and then will be 0 for some time, and again the next TS will start. So this period is nothing but TS period, and this period is nothing but DT period, and here the peak will be, let us say the peak goes up to here, up to I peak. So here it is N times I peak, because this is referred to the secondary side, and the slope will be falling where the slope is nothing but equal to minus N V naught by L, or you can say minus V naught by L, not N V naught, just minus N minus V naught by L, and this peak is nothing but NIP. Now this period from where to where the dB is in conduction, we will define this as d2 of t, and we know that we can write d2 of t is nothing but smaller than 1 minus dt. So we have dt and then d2 of t, and then we have some portion where neither the dB neither the S1 switch is on, and that is when the current through the inductor is 0, and that is when it is called as a discontinuous conduction mode or discontinuous operation. Now if we look very carefully, if we try to derive during this point, we can try to derive. So we can write during dt TS period, the slope is modulus Vs by L. So we can write modulus Vs, let us say modulus Vs of t is nothing but same as modulus Vs is nothing but we can write L IP, which is this value is IP divided by dt T of Ts period. Now this I can write I peak nothing but d of t Ts divided by L modulus Vs of t. Now if you look very carefully, the IP, the peak of the inductor current, or you can say the peak of the IL current, varies same as that of the Vd, or you can say modulus Vs, and that is when we can ensure that my current drawn by the flyback converter is actually following the sinusoidal pattern. So, we can get the IP value varies, a peak value of inductor current varies with modulus of Vst, and since it varies with modulus of Vs, so that means we can ensure that the current drawn from here is the modulus of Vs, that means from here it is the peak of the source current, or the current drawn from the AC source is also varying sinusoidally. Now this is, there is a correction, this is d of t times Ts here, and this is d2 of Ts. So now let us try to find out the average. If we define this as IL current, so let us try to find out IL average over Ts duration. Now if I try to find the IL average over the Ts duration, this is obviously referred to primary side we say, so it is nothing but 1 by Ts into half this in this area half times I peak, which is nothing but d of t Ts modulus Vst divided by L into the time duration, which is dt of Ts, and this, if we do that calculation, this and this will get cancelled out. That is when we get half d square t by L times modulus of Vs of t into Ts. Now if you look very carefully this particular thing, we can say that average variation of IL of Ts, if we over the Ts duration, average value over the Ts duration, if we say that, if we see from here, what we will get is, we can say that it is modulus of Vs of t divided by R effective, where we can write R effective is nothing but 2L by d square t into Ts. Now it indicates that the average variation of the current here is nothing but following the Vd, or you can say the variation, it is same as Vd, and Vdc's resistive load having the value, effective resistance value is nothing but 2L by d square t Ts. And this is something which we also want, because if we can see our previous discussion, if we can ensure that if the input impedance of this converter is a pure resistive load, then the current drawn from this source is also a sinusoidal. And we have seen that the average variation over the Ts duration, or over the switching period duration, the average variation is following the variation of Vd, which is nothing but rectified AC voltage, and it looks like that the converter looking from this side is having the resistive load value Re, which is nothing but equal to 2L by d square t of Ts, where L is nothing but the value of the inductance. We can write this L is value of inductance refer to primary side, or refer to winding P. Okay, so this we can say that if we can ensure that we have the resistive load at the output of the diode bridge rectifier, then we can ensure that the current drawn from the average current over the Ts duration is actually following the modulus Vs, and thus we can say that the current drawn from the source is having the unity power factor. Now if we see this particular circuit, we can do a very simple thing. We can just write a simple analogy where we can say that our, if we can say the average, or you can say the power at the output P naught, if we write, it is nothing but my V naught square by RL, where RL is my output load resistance. Similarly we can say that my input power is nothing but Vs peak divided by 2 R equivalent, and that we can assume the lossless converter, that means there are no losses in the converter. That implies my P naught is equals to P in, and that's when we can write down that RL by RE is nothing but 2 V naught square by Vs peak square. And this let us define this as, let us say, equation number 1, and we already know from here, or let's say this is equation number 1 and this is equation number 2. That's when we can see from 1 and 2 the RE, I can write down that as RL times Ts into d square T divided by 2L, nothing but 2 V naught square by Vs square peak. That's when we can arrange d square is nothing but, we can write down 4 V naught square Vs peak square, 4 V naught square by Vs peak square L by RL Ts. That's when we can write d of t is nothing but 4 V naught square Vs peak square under root L by RL Ts. That's when we can say dt is nothing but 2 V naught Vs peak under root L by RL Ts. Now in worst case scenario, my d of t is nothing but 1 by 1 plus, if we can, 1 by 1 plus Vs peak by n V naught, worst case. So if we define this as 3, this is 4, substitute 4 in 3, what we will get is, we will get 1 by 1 plus Vs peak by n V naught, 2 V naught by Vs peak under root L by RL Ts, and that if we rearrange this one, we will get L is nothing but RLTS divided by into n square divided by 1 plus n V naught by Vs peak square times 4. So this we can square it up, we can take this one here, so this will be 1 by n V naught Vs peak square. Now this is the critical value of L. This is nothing but L critical value, and if we see this one, this L critical value, we must ensure that this L has to be greater than, lesser than L critical to ensure the DCM operation. And if my L is greater than this L critical, then there will be a CCM operation, because the current will not fall down back to 0. The current, if we see here, the current will not fall down and becomes 0. So that's when we must ensure that the L has to be less than L critical for the DCM operation, and L has to be greater than L critical for the CCM operation. Now here if we see that L critical, we can write here, if we see that, if we just write L critical nothing but equal to n square RLTS 1 plus n V naught by Vs peak square times 4. Now this is referred to primary side. And if we look very carefully, if we make L less than L critical, then only DCM is possible. And if we can ensure the L, if we can ensure the L value to be smaller than the minimum L critical value, then we can always ensure the DCM operation. And when this L critical value is having the minimum value is when my RL is minimum and my Vs peak is at maximum. What I mean by that is sometimes the AC voltage also varies between minimum value to maximum value, and this RL is nothing but the load resistance. The RL minimum means you have the full load power, or you can say the peak power which you require from the converter. So, the L critical minimum value, so L critical minimum value has to be calculated for L critical minimum value has to be calculated for or you can say the peak power calculated for peak power demand and at maximum input voltage, not at the maximum value, or Vs has to be at minimum value and the, so the L critical, in order to have the L critical to be minimum, RL has to be minimum and Vs peak has to be minimum, and L critical minimum has to be calculated for peak power demand and at the minimum value of input peak voltage. And that's when if you select L should be less than L critical minimum, then it is ensured DCM is ensured. And why we need DCM? Because we need DCM because once we have a DCM operation, then we can ensure that the diode full bridge diode converter sees the purely resistive load, and that's when they have the purely resistive load, you will draw the unity power factor current from the source. Advantage what you will get is you have the isolation is incorporated, and you have the voltage follower mode. However, this particular converter can be used for low power applications. This generally for high power application the size of the coupled inductor will be huge. So, that is why this is limited to the or lower power level. Now, if we look very carefully, the flyback converter is the derivative of the buck boost converter. So, we can also have diode bridge rectifier followed by a, this is S1 switch and this is the inductor. So, on the other side if you let us say this is the source, so if you see when switch S1 is on, the current will be going in this way, since inductor current cannot absorb this one absorb suddenly. So, we have to ensure that the other side will be drawn. So, the other side will be there in such a manner that we have the load RL, and we have the capacitor connected like this, not plus minus, reverse way around, minus plus V naught, and you have the capacitance C. Now if you look very carefully, this particular circuit will be there, and this is a circuit dB, this is Vs equal to Vs peak sin omega t, and this is L inductor which I am talking about. So this converter can also be there, and here again one can ensure the DCM operation of this inductor, and thus this converter can be operated in a voltage follower mode, because the effective impedance looking from this side, effective input impedance of this buck boost converter will be input effective impedance will be a resistive, and thus the unity power factor current will be drawn from the source. So we can say that buck boost or flyback converter operated in DCM has the resistance, has resistive effective input impedance, and thus the current drawn from the source will be having sinusoidal variation. So thus if we can ensure that the buck boost converter or flyback converter operated in a DCM mode, then we can ensure that we have the sinusoidal current drawn from the source. Obviously in a, I mean the average inductor current in a switching period is having the sinusoidal variation over the line cycle, and at the same time the peak of the inductor current is also varying sinusoidal in nature. So this is the way we can obtain the power factor correction converter in case of single phase, or in case of when we have a single phase supply. We can either have the boost PFC based power factor correction converter, or we can have the bridgeless based PFC. We can also have some variation of the bridgeless PFC, but most commonly used are the totem pole based PFC. Then we can operate them either in a CCM mode or in a DCM mode. In DCM mode, the implementation perspective is, I mean from the implementation perspective it is very simpler. I mean when it is in DCM mode, we can ensure the voltage following characteristic. Similarly, we can also have the buck boost based PFC or flyback based PFC converter, and we can by ensuring the DCM operation of the buck boost converter or flyback converter, we can ensure the unity power factor current drawn from the source, and along with maintaining a constant voltage at the output. So that is what we have studied in some previous 10 to 12 lectures. We will carry forward our discussion, like we will see how the converters are there in case of three phase systems. We will start our discussions related to that from the next lecture. Thank you for patiently listening to this particular lecture.